Welcome back, everybody. Today, I'm going to give you several ways of thinking about modular curves, and I think you'll find this video particularly enlightening if you find modular curves confusing so far. Let's generalize the previous video first. If I give you a subgroup H of GL2 of Z mod NC that contains the negative identity matrix, and I know that the determinant map from H to Z mod NZ cross surge X, this will create a modular curve as follows. If K is the subfield of Q adjoin J and the end torsion of the universal elliptic curve fixed by H, then K must be the function field of a smooth projective curve over Q, which we'll call X of H by theorem 2 of the previous video. Okay, we'll call this a modular curve. So this X of H here, that's a modular curve. A modular curve X of H with function field K comes by the curve's field's correspondence equipped with a Q morphism from itself to P1, because we know we have an inclusion Q adjoin J into K, right? Because K is an extension of Q adjoin J. Well, inclusions of function fields correspond to morphisms of the curves, which these are the function fields of going in the opposite direction. And K is the function field of H, and Q adjoin J is the function field of the curve P1, the projective line. Okay, so I get every time I have a modular curve with function field K, I have a Q morphism from that curve to P1. Okay, we call this a structure morphism. Now, the points of the modular curve lying over J equals infinity in the projective line here, those are called the cusps of the modular curve. There are always only finitely many of them. If you remove the cusps from X of H, you get an affine curve, Y of H, which is written Y sub 0 of n in the case we've been dealing with X sub 0 of n as our modular curve, and Y sub 1 of n in the case we've been dealing with X sub 1 of n as our modular curve. So now let's consider things as Riemann surfaces. Let's let H star be H union Q and infinity, or just written H union, the rational projective line, if you like. Given a modular curve X of H, I can produce a subgroup gamma of SL2Z such that the Riemann surfaces given by the complex points of the modular curve X of H and the Riemann surface given by the orbit space of gamma acting on H star, this kind of extended upper half plane here, these are isomorphic. Let me make this precise. Let's let gamma in SL2Z be the transpose of the inverse image of H intersect SL2 of Z mod NZ under the natural entry reduction map mod N from SL2Z to SL2 of Z mod NZ. Then it turns out the complex points of the modular curve X of H are isomorphic to the orbit space of gamma acting on H star as Riemann surfaces. This is proven in Cornell, Silverman, Stevens, which I'll be calling CSS from here on out, chapter 3. In particular, we now see a strengthening of a fact that we already had. We see that the complex points of X sub 0 of n, you take that set, that's isomorphic as Riemann surfaces to the orbit space of gamma sub 0 of n acting on H star. And similarly, X sub 1 of n, its complex points are an isomorphism as Riemann surfaces to the orbit space of gamma sub 1 of n acting on H star. Okay, so we had these were bijections before, but this proposition guarantees me that there is actually an isomorphism of Riemann surfaces going on here. All right, now we're going to push towards kind of a big enlightening result for today. First, some notation. Let n be a natural number. For S, a subset of the complex projective line, denote by S sub 0 of n sub S, the set of isomorphism classes of enhanced elliptic curves, E comma C, for gamma sub 0 of n, such that the J invariant of E, this E here, is not in S. So remember, S sub 0 of n was the set of all enhanced elliptic curves. When I append to this a subscript S, what I want is, I just want, isomorphism classes of enhanced elliptic curves whose J invariant does not live in S, or S is some subset of the complex projective line. Let X be a complex modular curve. I've described for you how to get all of those just above. Let's denote by P1 of C sub S, the complement of S in P1 of C, and by X of C sub S, the inverse image of P1 of C sub S in X of C, the complex points of X, under the structure morphism mentioned above. Remember, I've got the structure morphism X to P1. So I'm saying that X of C sub S is the pre-image of P1 of C sub S under this structure map. Okay. Finally, I want to consider all pairs TC consisting of a one-dimensional complex torus T and a cyclic subgroup C of order n in T. So very similar to what we do with complex elliptic curves, which is no accident. And we'll say two such pairs, T1C1 and T2C2, are isomorphic if there's a biholomorphic group isomorphism from T1 to T2 carrying C1 to C2. It's the same way we define equivalence of enhanced elliptic curves, if you remember. We'll denote the isomorphism class of TC by bracket TC, and I'll label the set of all such isomorphism classes tori sub 0 of n. I can also make an obvious analogous definition for tori sub 1 of n. I'll just use points of order n instead of cyclic subgroups of order n. We'll call those points p if we need to. So we've got tori sub 0 of n and tori sub 1 of n. All right. Let's see, one last kind of technical remark before I give you the main result for today. If X is a modular curve and E is an elliptic curve over Q adjoint J with J invariant J, for example, if you can take E to be the universal elliptic curve E sub J, then E can of course be viewed as an elliptic curve over the function field of X, because that's, as we just got done discussing, an extension of Q adjoint J. Since a point X in X sub C determines a discrete valuation ring O sub X of the function field of X, why is that true? Well, you can just take the stock at X. You can just take the stock of the point X in the modular curve. If you don't know what a stock is from algebraic geometry, it's loosely speaking, it's like all of the functions on arbitrarily small neighborhoods of that point. That's a very rough description of it, but I don't want to get into the formal definition. Okay. The point is, there's like a nice little special ring associated to each point in this curve, basically because this curve is a non-singular complex curve. All of its stocks will be discrete valuation rings. Okay, and so because all the stocks are discrete valuation rings, it makes sense to ask the question, is this elliptic curve viewed as an elliptic curve over the function field of X? Can I talk about good reduction at each point of the modular curve? Sure. Because each of these rings is a discrete valuation ring, I can just say that E has good reduction at X if it has good reduction mod the maximal ideal MX in the stock O sub X. Okay. And there will only be one such maximal ideal. I mean, maximal ideals in discrete valuation rings completely govern the discrete valuation ring. Okay. So, if E does have good reduction, mod this maximal ideal M sub X, or we'll just say if E has good reduction at X, where X is a point in my modular curve, reduction mod MX gives a complex elliptic curve, which we'll call E sub X. That's what it means to have good reduction. You reduce mod something, you get another elliptic curve. Okay. If P is a point of order n on E and C is the cyclic subgroup it generates, so if C is bracket P, in other words, then the reductions P sub X and C sub X, so if I reduce P and C, those turn out to be well defined and they're still of order n. Okay, so I still get an order n point and I still get a cyclic subgroup of order n. Okay, so here's the enlightening result for today. I'll call it proposition 4. I'm just going by the numbering in my notes. Let's let E over Q adjoint J be the universal elliptic curve with J invariant J, or just any elliptic curve over Q adjoint J with J invariant J. Let's let S be any subset of P1 of C containing all of the places where E has bad reduction. So we want S to encompass places that we don't want to consider, basically, right? Fix an ordered Z mod NZ basis for the n torsion of E. Of course, you know you can do this because, again, n torsion of E is isomorphic as groups to Z mod NZ cross Z mod NZ. We'll call the second element of that basis P, and we'll let C be the group generated by P, the cyclic group of order n generated by P. Then there's an isomorphism of Riemann surfaces, X sub 0 of n with the orbit space of gamma 0 of n acting on H star, commuting the following square. I have the complex points of X sub 0 of n subscript S. So I define what that meant above. That was the pre-image under the structure morphism of P1 of C sub S, where P1 of C sub S is the complement of S in P1 of C. Okay, that is going to be sent via a map we're already familiar with to S sub 0 of n sub C sub S. Okay, which, I mean, we already know what this is too. This is the set of all enhanced elliptic curves for gamma sub 0 of n, whose J invariant isn't an S. Okay. Then we have a map going down to gamma sub 0 of n acting on H. So this is the orbit space. And then we have a map going to tori sub 0 of n. Now, what are all of these maps? The top arrow is a bijection. It sends a point X in my modular curve to the enhanced isomorphism class of elliptic curves given by E sub X, C sub X, the reductions of E mod X and the corresponding reduction of the cyclic subgroup C mod X. Okay, so this is a bijection. You've already, I mean, look, you've already seen this bijection before, right? This goes way back. We know that we can think of complex modular curves as parameter spaces of enhanced elliptic curves. I'm just saying that when you put this restriction on J invariance, you still have a bijection, which shouldn't surprise you at all. Okay, what's this bottom arrow here? The bottom arrow is also a bijection. It sends the class of Z in the orbit space of gamma 0 of n acting on H to the isomorphism class of C mod the lattice L sub Z, so that L sub Z is the lattice generated by 1 and Z for Z in the upper half plane, comma, the group generated by the n torsion point 1 over n, or specifically its coset 1 over n plus LZ. Okay, so you've got basically points in your orbit space in bijection with isomorphism classes of complex tori for gamma sub 0 of n. Okay, the left arrow is the restriction of the isomorphism we already know about. We already have an isomorphism from x sub 0 of n, its complex points, to the orbit space of gamma sub 0 of n acting on H star. So I'm just saying restrict that isomorphism to x sub 0 of n, its complex points subscript s. Okay, and the right arrow is also a restriction of a bijection. There is an obvious bijection from s sub 0 of n of C to tori sub 0 of n, so without the s here. And that map is just, you know, send an equivalence class of an enhanced elliptic curve E comma C to the isomorphism class of the complex points of E comma C. That's definitely a complex torus. We talked about that. That theory uses the Weierstrass phi function. And moreover, I just want to say, before I sort of give you a punchline here, all of the above is true. If you replace x sub 0 of n, s sub 0 of n, gamma 0 of n, tori sub 0 of n, C, and the group generated by 1 over n plus LZ, by x sub 1 of n, s sub 1 of n, gamma sub 1 of n, tori sub 1 of n, P instead of C, and 1 over n plus LZ instead of the group generated by 1 over n plus LZ. So you get another diagram that commutes. So what's going on here is essentially, more or less, you have 4 different ways of thinking about modular curves as complex curves. You can think of them Galois theoretically, like I just showed you how to cut them out from subgroups of SL2Z. You can also think of them as parameter or moduli spaces of enhanced elliptic curves. Okay. You can also think of them as orbit spaces of actions that various congruent subgroups of SL2Z have on the upper half plane. Or if you delete the S here, the action is on H star. Okay. Or you can think of them as spaces parameterizing complex tori up to complex isomorphism, each torus equipped with some kind of n torsion data. Okay, now that shouldn't surprise you at all if you know that complex elliptic curves are the same as complex tori. But again, I just think it's good to have knowledge that all 4 of these concepts of modular curves can be thought of in the same light. Like, not only are they the same kind of naively, but they commute an entire diagram if you think about them correctly. Okay, and so next time I will start talking about Heck correspondences, I believe. And so I'll see you then, and thanks for watching.